In this video we're going to talk about derivatives and graphing derivatives. A derivative, and I hope this looks really familiar to us, this limit as h approaches 0 of f of x plus h minus f of x all over h. This is called a derivative. And I know we've been calling it the slope finding equation, and that's very cumbersome, but that's what it does. It just finds the slope. The derivative, the answer we get when we do this limit, the answer is called the derivative. It's a function that finds the slope at any point. The derivative is the function that finds the slope at any point. Now, down here, I've written another definition of it that some books will use, and our book actually hits on a little bit, but not much. And it essentially is the same thing with a slight variation. Let me just remind you what ours says. Our definition says if we have a function and we want to find the slope at x, we go to another point really close to it, x plus h, and we find the slope between those 2 points. And this is where, you know, the top is f of x plus h, that's this y value, f of x is that y value, and the difference in the x's is h, so it's just the slope. Change in y is on top, change in the x is on the bottom, and we'd like the h to get smaller and smaller. That's the definition we've been working under. This definition says, let's say you want to find the slope at a point, call it A. So to do that, you pick another spot really close to it, and you find the slope between them. And of course, to find the slope between 2 points, you simply do the difference in their y values. F of x, of course, is that x value, or that y value. F of a is that y value over the difference. But to find the actual slope at the point, x should be getting closer and closer to a. So this x should be moving up towards a. Just like here, since h was getting smaller, this point was dropping back. So they really do say the same thing. We will stick with the classic definition that we've been using, this one, because you're good at it, we've been using it, and a lot of textbooks use this definition. So, to find a derivative, of course we can do the f of x plus h minus f of x all over h, limit as h approaches 0, but we actually have done this one before, and I'm just going to bank on the fact that you could actually go through and do it. You could do the limit as h approaches 0 of x plus h cubed minus x cubed all over h. The derivative is 3x squared. I'm going to write that over here, 3x squared. Now I want to just talk notation. We can notate the derivative a lot of different ways. We can say f prime of x, okay, and that it said f prime, and this little line here, this little mark means it's the derivative of f. Okay, so our f of x was x cubed, our derivative is 3x squared. Another way you'll see this written is y prime, because usually, of course, it's y equals x cubed while we're doing the derivative of y. The way I usually notate it is with what's called Leibniz notation, dy over dx. And the reason I like that notation, I'm going to put a circle around it because that's what I usually use. The reason I like that notation is because it really tells us what's happening. Okay, d is change in y, change in x, kind of like delta. Change in y over change in x. It's very clear that we're talking about the slope here. And 3x squared is our derivative. It's our slope finding equation. So dy dx. Now, graphing the function, the derivative, let me pull this in. I did this real quick. You might want to do it on your calculator. Of course, we know what x cubed looks like. It's in black. 3x squared is in red. And I just want to talk about their relationship really quickly. X cubed, you see here, has a positive slope. Okay, it goes from being extremely steep to not so steep, but it's always positive. So you notice its derivative is always positive, but becoming less positive. It's very positive here, just like the slope of x cubed, and still positive, but getting less positive. Here, the slope of x cubed is 0. That's also the derivative's value, 0. Here, The slope of x cubed is positive, so the derivative is positive. And the slope is getting bigger, so the value of the derivative is getting bigger. Now find the slope at the point 2,8. Well, to do that, we just plug 2 into the derivative. And again, I just wanted to talk notation. We could write f prime of 2. We could write y prime of 2. We could write dy dx at x equals 2. We could write all these different things. But of course, they all mean we plug 2 into derivative, and we get 12. Now this one is a little bit trickier to do the setup for. We do the limit as h approaches 0 of square root of x plus h minus the square root of x all over h. And to get this, we'd actually have to multiply by the conjugate, meaning the square root of x plus h plus the square root of x over the square root of x plus h plus the square root of x. And I'm going to rely on the fact you can do that, or you can look at that example. But let me get to the derivative. The derivative here is actually 1 over 2 square roots of x. Okay? So if I graph both of these things, the square root of x and 1 over the square root of x, here's what we get. The blue function, of course, is the square root, and you'll notice it always has a positive slope, but it becomes less positive. It kind of levels out as it goes on. So the derivative is always positive, but it becomes less positive. Here we have a slope that's almost, it's very steep, and it's actually exactly vertical right there. So you see the derivative is approaching a very large number, approaching infinity, because it's approaching this very steep slope. And again, to find the slope at 2, we just plug 2 into our derivative. 2 times the square root of 2. Finally, using what we know about the relationship between a function and the derivative, I thought it would be fun to try and graph a derivative of a really tough-looking function. This function is x times x minus 5 times x plus 5 times x minus 2 times x plus 2. So it's a pretty big function. Let's talk about how we'd graph the derivative. I always start with looking at the points where the slope is 0. Now the slope is 0 right there. The slope is 0 right here, and right here. And if the slope is 0, that must mean at those spots the derivative is 0. So I'm going to mark that in here. So everywhere there was a 0 slope, I marked a 0 for my derivative graph. Okay. Now in here, let's go between these first 2 dots. Here, the slope is negative. Well, if the slope is negative, the derivative must be negative. Now, if you think, well, how negative? Well, how negative has to do with what the slope actually is. If it's really steep and really negative, then it's really negative. If the slope's not very negative, then it doesn't go as negative. So that's kind of how you judge it. It's kind of just eyeballing it for now. Here, between these next 2 dots, the slope is positive. It's not real positive. It's not real steep. So my derivative should be positive, but not real positive. Okay? And again, if it were really steep, my derivative would get very large. All right, between these next 2 points, slope is negative, so my derivative is negative. Okay. Now we go to the ends. Over here, the slope is extremely positive. It's really steep there, so my derivative is very positive. On the other side, again, we're very positive. The slope is very positive, so my derivative is very positive. Okay, so I can kind of trace that all in one, smooth that out a little bit. There's the graph. of my derivative. And again, this helps us because there are some functions we don't know how to find the derivatives of yet, or that would be really cumbersome to do. So it helps to be able to get the idea of the shape without actually finding the derivative.